Okay, good afternoon, guys. Yep. Today, I would like to prove the other two Sylow theorems. Okay. Okay. And then we'll see how long that takes. Okay, so just to remind you, we have three Sylow theorems. Actually, first I should remind you what a Law of P subgroup is. So we have a prime number, and we have a finite group G. And then the order of G is like some power of the prime P, and then some number containing no factors of P. So P does not divide M. Okay, and then a Law of P subgroup of G is just a subgroup with this order. Is a subgroup H of G. The order of H is just P to the K. So it depends on what the order of G is. So like a Sylow 5 subgroup of a group of order 30 would be a group of order subgroup with 5 elements. A Sylow 5 subgroup in a group of order 75 would be a group with 25 elements. Okay. And what our first Sylow theorem tells us is that these groups always exist. Sylow 1, Sylow P subgroups exist. You know, in this situation where we have a finite group G with where P to the K divides the order of G. Okay. Sylow 2, it tells us that the Sylow subgroups, the Sylow P subgroups are all conjugate to each other. Okay. And the third Sylow theorem tells us how many Sylow P subgroups are there. So if NP is the number of Sylow P subgroups, then NP is congruent to 1 mod P, and NP divides M. And that's a Sylow, the 3 Sylow theorems. Okay, and we've shown this one. Now we need to prove that the Sylow P subgroups are conjugates of each other, and we need to find the number of Sylow P subgroups. And for these, I mean, I guess there's probably a lot of different proofs, but our proofs are going to use, we're going to use a group action with a P group. So that means we need to remember that if we need to remember the following theorem, if H is a P group acting on X, then we have the class equation, but for this, it says that the number of elements of X is congruent to the number of elements of the center mod P. Okay. And normally, you know, to motivate these proofs, we might try and like figure out like how, you know, they're kind of like they naturally follow from thinking about some group action. But actually to me these proofs are just completely out of left field, if you know what I mean. Like they're just I don't see how you would come up with this, you know. But that's okay. Like for the Law of Second Theorem, the group action you would use is not the one that I would think would work. So we'll see what I mean here. So let's prove Law of 2 first. We want to prove that Law of P subgroups are conjugates of each other. And actually our strategy is going to be to prove something stronger. So we have this theorem. Let's see. G is a finite group. P is a Law of P subgroup. Of G. And H is a subgroup of G, and H is a P group. And under these hypotheses, then H is a subset of GP G inverse for some G. Okay. So it tells us that any P group contained in G is actually contained in a conjugate of a Law of P subgroup. And now if H is also a Law of P subgroup, now if we can say if Q is also a Law of P subgroup, then we don't just get a subset, we get then Q equals GP G inverse for some G. Okay. And this is really, this is the statement of the Law of Second Theorem that any two Law of P subgroups are conjugate to each other. But we're going to prove it by proving this stronger statement. Okay. Okay. And here's what I mean. So normally, so if I see this theorem, what I want to do is I want to let the group G act on the Sylow of P subgroups by conjugation and see if something works out there. But that is not what you do. Okay, so let's see what we do. And okay. Okay, what we do is we let H act on X, which is a cosets of P, by left multiplication. In other words, for H in H and X, P in G mod P. Okay, this is just a set of left cosets. This is not necessarily a group because maybe P is not normal, and that's okay. But for a left coset and an element of H, we just set X times XP is just HXP. Okay. And of course, you know, we might worry about this group action being well defined, and let's not worry about it. It is. Okay. Okay, so we have a group action. My group H is a P group. So that means I get, so since H is a P group, you know, by the class equation, what I get is that the number of elements of X is congruent to the number of elements of Z mod P. Okay, and the rest of the proof is now just working to unravel this equation in terms of our group H and the set that the group acts on and the Z. So let's just kind of unravel everything. First of all, what is Z? These are just the elements of X fixed by every element of the group. So these are the XPs satisfying HXP equals XP for all H. That's what Z is. Okay. What does that mean? We rewrite this condition. One way to rewrite it would be to say that let's see. How should we rewrite it? Let's just do some scratch work on the side where we want to figure out what this means. So HXP equals XP. Well, that just means that another way of writing that is hx is equal to x times little p, or not p, h times g for some g and p. Another way of writing that is that x inverse hx is equal to g, which is some element of p. So what we want to say is that this condition is really the same as saying that x inverse hx is in P for all h in H. Okay. So that means this z, it classifies which x's. Oh yeah, and we can rewrite that last condition. We can rewrite it as x inverse hx is contained in P. Okay, so one way to rewrite Z is as the left cosets such that the representative x inverse hx is a subset of P. Okay. Now if Z is non-empty, our goal now is to show that Z is non-empty. If it's non-empty, then XP and Z satisfies x inverse hx is a subset of P. In other words, H is a subset of XPX inverse, which is what we wanted to show, right? So if we can just prove that Z is non-empty, then we're done. Okay. And so one way to prove that Z is non-empty is to prove that it's not equal to 0, that size is not equal to 0. One way to prove that its size is not equal to 0 is to prove that it's not congruent to 0 mod P. Okay, now we need to look at the size of X. But X is just the number of cosets of this C Law of P subgroup P, which is the index. The index is just the size of G divided by the size of P. Size of G is P to the K times M. Size of P is P to the K, so we get an M. Okay, so the number of elements of X is M, and P does not divide M. This is, since this is just by definition of C Law of P subgroup. Okay. Okay, so P does not divide M. P does not divide the number of elements of X. So therefore, the number of elements of X is not congruent to 0 mod P. And therefore, the number of elements of Z is not congruent to 0 mod P. Therefore, the number of elements of Z is not 0. If it were 0, it'd be congruent to 0. Okay. Therefore, Z is not empty. And that's the end. Because when Z is not empty, then take an element of Z and it satisfies that H is contained in a conjugate of that P, that conjugate of P. Okay. So, I mean, this proof is, it's, you know, it doesn't waste any time, I guess. But still, if you ask me, like, how does this proof work? I don't really know. Why I don't really know why this works or how whoever it was came up with it. Which is unfortunate. Okay, but oh well. Okay, so anyways, this proves the law of second theorem, which tells us that all the Sylow of P subgroups are conjugate to each other. Now, this gives us kind of, this tells us if we know the number of Sylow of P subgroups, if the number of Sylow of P subgroups is 1, then the Sylow of P subgroup is normal. And if the Sylow of P subgroup is normal, the number of its conjugates is exactly 1. Okay, so we can kind of try to use, now with the Sylow third theorem, that allows us to use like arithmetic to try and figure out if G has any normal, any Sylow, any normal Sylow P subgroups. Okay, so let's try and prove the third theorem, which requires us to count, let's try and count the number of Sylow P subgroups. Okay, and again, we don't use conjugation, well, first we look at the action on the left cosets by translation, and then we look at conjugation. Before I move on to this next part, let's just do an in-depth look at the following property. Let's just call it a proposition. You know, H and K are subgroups of G. And let's just try and show that and then G is an element of G. Let's try and figure out that HGK equals GK for all H, if and only if G inverse HG is a subset of K. Okay, because we did use it in the last proof, and also I kind of explained why in the margin, but maybe we should just like be careful because we're about to use it in the next proof as well. So let's prove this little mini result. Okay, just to be safe. Okay, let's suppose HGK equals GK, oops, for all H and H. Okay, what does HGK equals GK mean? It just means that HG and G are in the same left coset of K, it just means that HG is equal to GK for some K. Okay, and then we just multiply both sides by G inverse. So G inverse HG is equal to K for some K. In other words, G inverse HG is in K. And then this is true. This is true for all H and H. So if we add that in, we're okay. Okay, in other words, G inverse HG. So everything like this is an element of K, so this forms a subset of K, which is what we want. Okay. Okay. So now this proposition is why we might look at H acting on the left cosets, because that action tells us something about the conjugates of H. Okay. And now we're going to use kind of a similar action. We're going to try and prove something. Let's see. Let's try and write it down. Okay. Let H be a P group. So a subgroup of G, which is P group, meaning it has like P elements or P squared elements or P cubed elements, etc. Right? And then just based on that knowledge, then the index of the normalizer of H, the index of H and the normalizer of H is congruent to the index of H in G mod P. Okay, let me remind you what is the normalizer of H. The normalizer of H, that is all the G's such that GH, G inverse equals H. In particular, H is normal in the normalizer of H. And so if H is normal in G, then the normalizer equals G. Okay. So let us take just a 5-minute break. We'll prove this and we'll see how that relates to the number of conjugates of our Law of P subgroups. Okay, so yes, just see you guys in about 5 minutes. Okay.